Welcome back. In the last video, we covered the two topics of validation curve as well as learning curve, which is really to deal with the issue of variance as well as bias trade-off. In this video, we're going to go into cross-validation. In particular, two specific concepts that I want to cover is called holdout cross-validation as well as k-fold cross-validation. Now, a test set should still be held up for basically final evaluation, but the validation set is no longer needed when doing cross-validation. So I just want to highlight some concepts here. In the basic approach called k-fold cross-validation, CV stands for cross-validation, the training set is split into k smaller sets. Now the following procedure is followed for each of the k-folds. A model is trained using k-1 of the fold as training data, so that leaves one fold not touched. So that means the resulting model is validated on the remaining part of the data. Okay, so this is where it's used as a test set to compute the performance measurements such as accuracy or score, R-squared score, for example. The performance measure reported by k-fold cross-validation is then the average of the values computed in the loop itself. So that's really the scikit-learn explanation. So I'm going to go into each of these holdout and as well as the k-fold cross-validation in a little bit more detail. I pays to actually explain this and take some time to explain this because this is really a very important concept. So the holdout method works like this. You have the original data set and you split it into two portions. You split it into the training set as well as the test set. The training set is the set that you use to train your model. After you've done with training your model, then you use the test set to estimate your model's ability to generalize with data that it has not seen before. So this is really to allow you to get an accuracy, get an estimate of how well it will perform in the real world. There's a variation to the holdout method. The variation is to split the training set to two, not necessarily equal proportion or half-half. The training set is split into, again, another training set and a validation set. So the training set is really, again, as I mentioned before, for training your model, for fitting different models. The validation set is for tuning and comparing different parameter settings to further improve the performance for making predictions on unseen data. And finally, for model selection. Now we cover a little bit of this validation earlier when we cover the validation curve as well as the learning curve. We did actually make use of it. So this is really where the basic concept comes from. So just to highlight again, validation set is what you use for model selection. Now this process here is also called model selection. Surprise, surprise. We want to select the optimal value of tuning parameters, also called hyperparameters. So this is what it looks like. You have the original data. The holdout set looks like this. Holdout method, but basically you have the test set being holdout for you to validate. But the modification of that is basically you have a training fold, and then you have another portion here is what we call validation set. An improvement to that is called k-fold cross-validation. So basically it's taking it one step further. So let me just highlight this. Not so much highlights as such, just put this in because CV is everywhere. If I don't do that, it's going to get confusing. What is k-fold cross-validation? It randomly split the training data set into k-folds without replacement. Now, k-1 folds are used for the model training. The remaining one fold is used for performance evaluation. Okay, so the k1 folds are used for model training and the one fold is used for performance evaluation. So let me just illustrate this. We have the original data set as mentioned before, you have the training set, you have the test set. So now we are just playing purely with the training set. The training set is then split into two portions, the training fold as well as the test fold. So you have, in this case is what we call a 10-fold. So you have 9-fold is used for your training, and then you have one fold is called the test fold also called the validation for. Okay, so the next loop, you take 1 all the way to 8 and 10 as your training for, and the number 9 is your test for, or the validation for, and you repeat this for 10 times until the first for is being used as your test for. Okay, so that's really the idea here. This procedure is repeated k times. If it's 10 times. The final outcome is that there will be k models and performance estimates. You calculate the average performance of the models based on the different independent folds to obtain a performance estimate that is less sensitive to the sub-partition of the training data compared to the holdout method. Because you've done this 10 times, it's going to get a better estimate rather than just doing it via the holdout method. Now, the K4 cross-validation is also used for model tuning, fitting the optimal hyperparameters value. In the example in our previous video for the ridge regression, we use alpha. Okay, so finding the optimal hyperparameter values that yield a satisfying generalization performance. Once we have found a satisfactory one, then we can retrain the model on the complete set of data to get a better performance. Okay, so the whole rationale of doing that is that the whole training data after K4 cross-validation is to provide more training samples for the learning algorithm. Usually this results in a more accurate and robust model. And 10 is actually quite a common one. For a relatively small training set, you may want to increase the number of folds above 10. There's a variation of the K4, is the stratified K4 cross-validation. It can use better bias and variance estimates, especially when you are dealing with unequal class proportion. So we're going to cover class in the next classification in the next section. We will revisit this stratified K4 cross-validation then. Right, so let's do some enough theory. Let's do some codes. This is an example that I kind of modified from Scikit-learn. Scikit-learn did it on a different data set. I'm going to just continue with our theme on Boston housing price data prediction. I'm just going to continue with that theme here. So here it's adapted from Scikit-learn. So learning the parameters of a prediction function and testing on the same data is a methodical mistake. That part is really important. So what we have done, as we illustrated earlier, is to split our data into train and as well as test split. Okay, so let's just run this code here. So we're using support vector machine here. We download the data for the Boston, and we're keeping 40% as our test set and the remaining 60% as for training purpose. Okay, so if you look at the regression score, it's rather low at 66%, but that's okay. This is really for illustration purpose rather than for the actual trying to get a perfect score for production purpose. So when we're evaluating different settings, which is the hyperparameters for the estimator, such as the C settings for support vector machine, is actually a manually set. There's still a risk of overfitting because the parameters can be tweaked until the estimator perform optimally. Now we've seen this in the validation curve earlier in the earlier lesson. Now this way, knowledge about the test set can leak, so quite often we don't touch the test set. So we do that with the validation, which is the K4 that we talked about earlier. All right, so we hold out part of a data set can be held out as so-called validation set. Training proceeds on the training set, after which evaluation is done on the validation set. Okay, so by partitioning into 3 sets, we drastically reduce the number of samples which can be used, and the result can depend on particular random choice of the pair. So that's why we don't do it this way. Instead, we use the K4. All right, so we'd already touched on K4, so I won't walk through this explanation. Instead, we're going to dive into the code itself. And okay, so let's look at this. So you have model selection. We're using cross-validation score, and we're running the regression or support vector machine. And this is the cross-validation score method that's provided by Scikit-learn. We've already imported that. And provide the regression or the regressor, which is the support vector machine. Provide the data. Okay, if this is the X, this is the Y. Oops. And here we provide and request for FIFO cross validation. Now once we run that, okay, so let's just wait for that to finish. This can take a while depending on the complexity of the model itself, as well as the how many cross validation or how many fold that you've done. Okay, so this is what it is, and we calculate the mean score, which is rather low at 45%, and the ones, this is 2 standard deviation, is rather large. It's really large. Okay, so the next thing that we can do is actually we can use the negative mean square error or the mean square error, but we put a negative there so that it actually goes the same direction as the R square. And when you actually calculate it out, so this is the score that you have. So you can actually take a mean of that and you calculate the standard deviation as you did using these. This is not really accuracy, it's more the score. In this case, because we are using the regression, so it's going to give you a slightly different number from if you're using or applying it to the classification. This portion here, this is R square, okay, and this portion here is the mean square error, except that it's been flipped with the negative mean square error. Alright, so obviously there are a whole lot of other so-called metrics that you can use, but for now we just want to look at these two. Right, the other thing that I want to highlight is the K4. This is really cross-validation. Okay, so looking at K4, K4, as we mentioned before, basically chop the bits up and leaving one fold for validation purpose. So let's just run this. You can see that the K4 built-in function provided by scikit-learn split it into two, and what you have here is you have the train and test set. Alright, so that's really how the actual splitting is done. Right, looking at the stratified K4, it's a variation. We talked about that a little bit earlier. It's useful for uneven class problems. This is an example of a threefold cross-validation on a dataset with 10 samples from 2 slightly unbalanced. And notice that you have 1, 1, 1, 1, 1, there's 6 of these, and there are 4 of these. Alright, so as we run this, notice that it actually split this way. Alright, so that's really what stratified K4 does. And these are the index number, by the way. Okay, so now that we actually run through and look at the subplot vector machine, except this time around, we are looking at the prediction itself, or the accuracy of the prediction. Again, we are actually doing this on support vector, and we're fitting and calculate the actual score itself. Let's print it out. The accuracy is quite low. If you look at the cross-validation, what you see is the whole range of data that it actually output. And if you look at the so-called mean score versus the standard deviation, it's not very exciting. But the purpose of this is to not so much look at the how well the model does, but to illustrate to you how stratified K4 is done, whereby what you see here is that the actual splitting is actually a little bit uneven, and the other one is that it's actually split the data and shuffle it, really, in another way to look at it. We also touched on K4 already. So with that, I'm going to stop here. I'd like you to actually conduct an exercise and do it this time around with the Boston data or another set of data. It doesn't matter. The point of this exercise is to actually change your test set, maybe to 0.8, okay? Sorry, 0.2, test size to 0.2, and leaving 80% of your data for training of your model. And run a cross-validation matrix such as this, and see how the actual steps is done, and just try to get a feel of how the whole process works. So pause the video now and run that exercise. When you come back, I'm going to wrap up today's lesson. Welcome back. I hope you have found that exercise improve or cement the lesson that we've covered. What we have covered in this lesson really is the concept of holdout cross-validation, as well as K4 cross-validation, and illustrate to you in pictorial format what a holdout method looks like, what the K4 cross-validation look like, and how it can be used to actually evaluate your estimator's performance, and provided some codes for you to actually get a rough idea of how it works, and also hopefully you did the exercise to actually allow you to understand how the cross-validation score functions. It's inbuilt into Scikit-learn, to actually get a gauge of how the process actually works. With that, I'm going to end this video. I look forward to seeing you in the next video. I've got something exciting that you will love, you will enjoy. I look forward to seeing you in the next video.